afternoon session on the second day of this wonderful conference workshop. We do want to keep enough time for discussions. That's a very good part of the talk. So I will tell you 5 minutes before the end. Okay, so the first talk of the session is by Yao Wang from Clemson University, and that's the title.
Thanks for the intro. So, is there a mic or?
No, we don't need a mic.
Oh, you don't need one. Oh, I see. Okay, great. So, yeah, thanks for coming to my talk. I will talk about the manifold effect of the single hole problem to the Hubbard. It's a more generalized Hubbard in the end. I want to cover 2 subjects. One is what many of the speakers have discussed in a codecum system in the single band Hubbard. What happens with the single hole and the spin program problem and breakdown spin program. Then in the second part, I will move a little bit fast for the first part, and I think overlap with a lot of the speakers. For the second part, I want to talk about a extremely correlated system with a single hole in the extremely correlated Hubbard model in the quantum dot simulator that will lead to the Nagauka and Nagauka condition. I want to acknowledge my collaborators, especially 2 experimental groups, the Emmanuel Bloch group at the Max Planck Institute, MTQ, and also that's for the codecum project, and also for the quantum dot project. I want to acknowledge Steven Wenderstein group of the UW, and also a lot of my theoretical collaborators, organizer of this meeting, Fabian, Annabelle, Eugene, and also okay, so let's go back to, of course, the way of the knowledge funding agency. So although the Hubbard model has been a kind of old topic almost 100 years ago, the people started to become interested in it because of the ITC implementation. After the discovery of ITC, people can overcome the Babinda limit and increase the TC to 130 Kelvin. That's an important discovery, which leads to a lot of applications. The unconventional property of the high TC cuprate lies in multiple aspects. One aspect is that they have the D-wave pyrosymmetry, and that's different from the traditional BCS theory. And there are a lot of interesting discoveries because of cuprate. In the cuprate phase diagram, there are a lot of complicated phases like field gap, grid metal, stripe, charge order. This is a complicated phase diagram that has been quoted like 5 times at least in this workshop. The complexity of the phase diagram also gives us a way to revise our model, our understanding of strongly correlated electrons. So the first thing we will notice from the phase diagram is that there is antiferromagnetism at the parent compound, which has 0 doping. That indicates, that kind of hints the strong correlation Hubbard model mediated with antiferromagnetism may play a role in the entire cuprate. So that leads to all the assumptions using the Hubbard model. But this can actually derive from the ab initio perspective. We can start from the crystal of cuprate and extract the greatest common divisor, which is the copper oxide plane. And the chemistry tells us we have the strongly correlated charge transfer insulator. We have the copper separated by Coulomb and oxygen in the middle. Then the bonding of the copper and oxygen give us the genre singlet band. That can be projected to the single band model. We get the single band Hubbard with only 2 or 3 parameters, depending on whether you add the E prime. We basically have the strong Hubbard U acting on the band structure of the electron. So after all this, kind of from ab initio chemistry, we can conclude that the single band Hubbard may be one of the key problems in cuprate. So this is the discussion has been lasting for 30 years. And let's see, in the Hubbard model, although it has only 2 parameters or at most 3 parameters, it can actually reproduce a lot of experimental discoveries. In the phase diagram, we know that it can, we already know and learned in the morning session, Hubbard model can partially reproduce superconductivity, D-wave superconductivity, the closely long range order in 6x ladder or extrapolate to wider systems. Hubbard model can reproduce the antiferromatism. Hubbard model can give you the signature of the pseudo gap. And Hubbard model can also explain some newly discovered phenomena like the stripe, also related to some more some more physics like the string metallicity, quantum criticality. So these are all discussed in the context of Hubbard model. But I want to see that although there are still some debate whether Hubbard model is sufficient to incorporate, or we can draw the phase diagram or the diagram like this, the high PC may contains the discussion of a Hubbard model, but they may include something else like the multi-band issue and pronouns. But the Hubbard model itself, as the model for correlated electrons, is way beyond corporate. It actually has a wider application. We can put Hubbard model in a triangular lattice in the frustrated system. We can get spin liquid, or we can use a strongly correlated model, and we can describe the non-thermal quantum state, manifold localization. And the Hubbard-like interaction between multiple bands can lead to exciton, which is crucial for a solar cell, charge transfer solar cell. And even for chemistry and the biochemistry problem, for the catalyst and enzyme problem, the key point is still the active site, the transition metal in the middle. That's still a multi-band Hubbard model. So Hubbard model is actually everywhere. The solving Hubbard model seems to be solving an entire range of the different problems, and way beyond the corporate itself. So, but solving a Hubbard model itself is very complicated because of the strong correlation and the entanglement due to the strong correlation. If we just account the possible electronic configurations, due to the strong entanglement, we have to solve a combinatorial problem. The Hilbert space is combinatorially large. So for n orbital system, the Hubbard model has a dimension of 4 to the n, and the computational complexity for such a matrix is even higher. So that leads to the idea, why not using a quantum simulator instead of a classical computer to solve it? That attempt is that solving a Hubbard model using universal gate-based quantum computer using the variational answers. That's one aspect of the attempt using the hybrid quantum classical method. It's still limited to a very small Hubbard model, on the order of 8-side Hubbard model. That's still not comparable to the classical computer 30 years ago. The main topic of this workshop, which is the leading effort in simulating Hubbard model, is actually the analog quantum simulation. So we know that in using code atom in optical lattice, we can use it to simulate a single band Hubbard model with up-down spins. We can use the quantum gas microscope to reach high resolution snapshots, a single site result snapshot. We can resolve a lot of the statistical correlation functions that give us the high resolution controllable and measurable platform. I also want to mention another quantum simulation platform which hasn't been covered yet in the workshop, which is the gate-confined quantum dot. That's actually an older generation of the analog quantum simulation of artificial molecules. Basically, you can grow the electrodes on top of the surface of the clean semiconductor. Then can solve the boson equation. The electrostatic potential will give you a lot of quantum wealth on the order of 100 nanometer, and that can be regarded as the large scale atom. That's a simulation of the correlated electrons using a large scale electron. You can tune the gate voltage to control the size and of the hopping, similar to the optical lattice. But it uses electrons to simulate electrons. So naturally has a long range Coulomb interaction and also has a multi-band nature. I want to mention both of the quantum simulations in my talk. So let me start with a simpler one, the single band Hubbard model, and use the quantum simulation of the optical lattice as a transform. So I want to restrict myself to physics near half fading as more easier to understand. In near half fading, we know that the Hubbard model can be projected to the TJ model using the super exchange. We get the J equal to 40 over U, 40 squared over U by the second order super exchange process. And you can do a straightforward transformation, and you get the TJ model with additional terms. We usually ignore these additional terms for many reasons. TJ model gives us a perspective, an insight to understand the physics of Hubbard model at low energy. But I will just use it as a guide of the intuition. I will only simulate Hubbard model in the remaining of my talk. So let's see what TJ model or the low energy Hubbard tells us in a single hole limit. If we look at the
interplay of the kinetic energy and the on.
Is that a question or? Okay. When we have a single hole node in the system, in a 1D system, it's like we eliminated the electron in the antiferromagnetic background. And due to the kinetic energy, the hole will move, and the motion of the hole will generate a spin wall with parallel spin, which is energy unbearable. But due to the topology of 1D, you will never generate a second domain wall when you move the hole further. So the motion of the domain wall is controlled by J, and the motion of the hole is controlled by T. So they will separate from each other. This phenomenon is called spin charge separation. You will not increase the energy by separating them. That's just an effective picture in the lowest energy. But when we have a single hole in the 2D, the situation is slightly different. You still have the whole motion generated domain wall, but it will generate a sequence of domain wall, which with the energy cost parallel to the step of the whole motion. So you cannot keep moving like this if energy forbidden. So in the end, you have to wait until the spin defects to heal themselves, because the spin interaction is not only Ising type, Heisenberg type. You can flip the spin, the nearest neighbor spins. So you can wait until the spin to heal themselves. So that's a much lower speed, a much longer time scale. So the whole motion is trapped by the cloud of the spin defects. That's a picture of the spin polygon. So in the end, it seems like the whole motion is associated with a cloud of defects in like a polyronic picture. So we call this entire subject spin polygon of this normalized orthogonal weight. So such a picture is very similar to the idea of the BCS, the photon polygon, when we start to talk about pairing mechanism. So when you have the polyronic effect, two electrons may want to share the effect in the background. So that will be helpful for the pairing. That's why we start to discuss the spin polygon. It may be related to the pairing mechanism. Okay, so once we have the spin polygon, we can try to detect some quantities, but it's not very easy to measure the spin polygon itself because it's intrinsically not a two-body polygon. If you measure the spin correlation, you will get the anti-ferromagnetism. The nearest neighbor spin correlation will be anti-parallel for the remaining of the background, and it's only parallel when we're in the polygon regime. So if you just average over all the sides, you will just have a reduced number, slightly reduced number of the correlation, and that won't help you to detect the polygon itself. So that requires us to use the higher order 3-point correlation function, which we chose the co-moving frame of the hole and try to calculate the correlation between the co-density times the nearest neighbor spin correlation. That will help us distinguish the position of the spin defect. Okay, so using this idea, we can try to measure the 3-point correlation measurable in photoatoms. But we should also pay attention that not all sides near the hole are parallel. There are still some neighbors being anti-parallel. So we want to subtract off the background to make the contrast of this spin polygon signature. So if we subtract off the background, we will get a positive value, which means it's being easier to be aligned near the hole when we have the nearest neighbor spins. So that will give us a positive signal by calculating the connectivity. That's why finite temperature exacerbation. And another signature you may notice is if we calculate the diagonal spin correlation, it should be parallel in the spin AFM background, but it should be anti-parallel if we have the spin polaron defect. So that means if we do the same thing for the connected part of the correlation, we can get the negative value for the diagonal bound near the hole. So these are the two signatures we can use to signal the presence of the spin polaron. As that has been verified in used both numerics and also in experiments. This is the simulation we did 2 years ago for a 4x4 system in the finite temperature examination. Of course, there are a lot of other simulations at the same time. And more importantly, it has been, I'm not in this paper, but this has been a milestone work using quantum gas microscope to signal the presence of the spin polaron. You can see the negative, strong negative value in the diagonal bound near the hole. We use the double, it's equivalent to the hole. Okay, so knowing the presence, the fingerprint of spin polaron, we can try to discuss the breakdown of spin polaron in multiple physical regime. We can try to dope the system. If we dope it, let's try to track these the neighboring correlations. When we dope it slightly, we still get the spin polaron. We have the negative values for the diagonal and the positive for the horizontal and vertical bounds. If we further dope it, they become weaker, but the pattern, the sign is still correct. But if we dope it above 20%, you start to see that the sign violates the prediction of the spin polaron. So that's the signature of the spin polaron breakdown. So if we just extract the horizontal and vertical bounds, the one that should be positive for spin polaron, we can track the experiment done by the Emmanuel Bloch group. You can track the evolution of this correlation as a function of doping. So at half filling or lightly doped system, you still get a positive value. But when you cross 20% doping, you start to be negative. So that's the signature to break down at 20%. You can reproduce the result using the small cluster EE simulation. And what's more important is we can actually compare different regimes by different theories done by Fabian and Annabelle. If we compare the result with the spring enzyme, which is the behavior, the nature of the spin polaron, assume that the scramble of the spin defects, you will have a pretty good comparison below 20%. And above 20% doping, the heavy dope case, you can actually make a good comparison with the free fermion theory. So that means it's actually we basically understand what happens near 20%. Below 20% doping, we have a spin polaron, and above it, the spin polaron just disappear. We can also, so this is the picture. We can also test the temperature dependence, and the temperature dependence in theory tells us the crossover is almost independent of temperature. No matter how you increase the temperature, the crossover always happens at about 20% doping. So that reminds me of the APAS experiment by the X group in Cooperate. They found that at 19% doping, no matter at which temperature, there is a crossover from the non-caustic particle picture to a caustic particle picture. So it may be associated with the breakdown of the spin polaron. There's no definite proof. Of course, you can try to break spin polaron using a different way. You can add impurity. You can add charge impurity into the system. This can be simulated, of course, by the optical tweezer in cold atoms. This is the result. If we have no impurity, that's what we presented before. We have the perfect spin polaron signature for a single hole, so Hubbard. But once we start to add impurity in the center, we start to tap the hole. Then the hole becomes not mobile. that will not give you the scrambling of the spin excitation. So you can see the sign of the neighboring correlation just flip, and the flip to positive for the diagonal and negative for the horizontal and vertical lines. And you can also draw the picture of the trapping potential as a function, the 2D phase diagram of trapping potential and temperature. They actually play against each other. The temperature wants to delocalize the hole, and trapping potential wants to localize the hole. So that can be, we can sketch the phase diagram. We have the spin polaron being destroyed by the trapping impurity, and it's for different temperature, but no matter how you change the temperature, the doping excess doesn't change. You still have the 20%. Okay, so I actually intended to talk about the high order correlation, but I think I will skip it to the time limit. The basic idea is in the spin polaron physics, there are actually something beyond the third order correlation. We have let's work together with Fabian and Annabelle. We found that the 5-point correlation is actually has a very dominant value in this connected part. So this is comparison for the connected part of the 5-point and the bare 5-point correlation. That's because of you can understand it by the string picture. And it can also also signal the breakdown of the spin polaron with the presence of the impurity. Okay, I'll skip the discussion about high order. It's another more complicated subject. So let me switch to the situation when we have the extremely strong correlation. We know that in the typical Hubbard model is equal to the bandwidth. We have antiferromatism and we have the spin polaron. But once we have strong correlation, extremely strong correlation, the physics may change. It's called the Nagoka phase. So the Nagoka theorem tells us when we have extremely strong correlation, U is much bigger than the bandwidth, and when we are very close to half fitting, it's basically a single hole picture. Then we have the interference of the kinetic energy power. So the basic idea is if you have the ferromagnetism background, then when you move the hole in the background, you will have the interference of different patterns. You will get the same pattern after you move along the loop. So that will give you a benefit in the kinetic energy. But if you have an antiferromatic background, you will not gain this kinetic energy because we correspond to different configurations after you move in the loop. So that means the ferromagnetic state is more favorable due to the past coherence. That's the Nagoka state. So this is actually mathematically proven in a thermodynamic system with infinite U. But it can also be realized in the small size, in the finite size system. There has been some earlier work showing that in the 2x2, that's the 4-side Hubbard model, you can easily solve it by hand. In 1 minute, you can show that for a 4-side Hubbard model, the critical U is about 18 T. So that about this U, we will have the Nagoka phase. And this can be realized in quantum dot system because in quantum dot we can control this U at a very large number in a few size. But in quantum dots, it's a little bit more complicated than Hubbard model. We not only have the Hubbard U, we also have some long-range interaction because the electron will have a longer range Coulomb. So this is a simulation picture in a 4-side system with a little bit longer range interaction. You can see that so the x-axis is a hopping. So we fix the U and change the hopping. So at hopping equal to 0, they are just a disconnected size to have equal energy for high spin and low spin state. But when you increase T, that means you suppress the U over T. Ultimately, you will cross the boundary and you will have a transition between the high spin state and the low spin state. So that's the 2 states in the blockade 2x2 blockade system. So that's in the single band limit. But you may realize in the quantum dot, 5 minutes. Okay. In the quantum dot situation, it's not necessarily single band because we have the tracking potential. You have to really consider whether excited state will be involved. So we actually did the estimation and found that the level of spacing is actually smaller than the Coulomb repulsion. So that means you have to really consider the multi-band nature. generalize the Nagoka theorem to multi-band system. So in order to do that, we set up an entire framework using a mesoscopic ab initio calculation. I want to skip the details, but the basic idea is we construct the orbital basis using a quantum dot, quantum well system, the bound state in the quantum well, instead of using the bound state in the atom, because in large scale you won't see the structure of the atom. Then we just solve the different bound states in different quantum dots and use the same trick we did in quantum chemistry in the configuration interaction. We can orthogonalize these kind of quote-unquote atomic orbitals into the one-year orbital. Then we construct the many-body basis using the one-year orbital. That's the same rule, same philosophy as the quantum chemistry. Then we can calculate the many-body model by doing the integration, single particle or the single electron or two electron integral. We can calculate the crystal field fraction to the side energy. So the side energy is not necessarily the single quantum well side energy. Calculate the Hawking term, which decays exponentially with the distance between quantum dots. We calculate the local interaction and the non-local interaction. There are some tricks. You can see that after we calculate the side energy and the local interaction, you can see the local interaction Hubbard U is always bigger than the level spacing, and the dark E spacing between side energy. So that means it's really multi-orbital, and we can also add long-range interaction. So then we can do the full configuration interaction, full CI simulation. We call it ab initio indeed to distinguish from the chemistry. Let's start to add different terms one by one. If we just restrict ourselves to local interactions, so T, U, J. J is the home term, it's not the super exchange. That's called multi-plane model on the single side. We do not have long-range interaction. So on this level, you already see that the high spin energy is lower. So it's already a Nagoka state, and the Nagoka gap is 2.2 mu eV. And if we keep adding long-range orders, long-range interactions, and try to mimic the realistic condition, you may change the value of the Nagoka gap, but the high spin state is always the winner. The situation is slightly different when you add long-range exchange interaction. So that will change your that will affect your the spin alignment in parallel and anti-parallel. So you start to have a larger Nagoka gap. But according to the comparison, we found that the Nagoka gap with local interaction is already dominant. It already takes 80% of the total Nagoka gap. That means the physics is dominated by the exact continuity instead of the long-range home interaction. So it's really a multi-orbital generalization of the Nagoka theorem. So this can be realized in quantum dots. So this is a typical picture. All quantum dot experiments will show you the charge stability picture in semiconductor. You can tune the gate voltage to move from a double occupancy state to a singly occupied state. Then you can tune you can do the detuning of the potential. This picture shows how you should expect in the detuning. You should expect the level crossing between the single occupied state and triplet state, singlet state and triplet state. So that gives us a way to detect the Nagoka phase in quantum dots. This is done by when we do the detuning from the known state to the target state. We can actually do that very fast in a diabatic way. Then in this case, you will always follow the same state. You will not have time to cross the transition to flip the spin. So that will give you this curve. So you will see that there is a suppression in the middle because you are in the middle of the level crossing. But if you do that very slowly, adiabatically, you will see that you will always get a high percentage of the triplet proportion. So that means you always keep it at the ground state. So the separation between the two curves tells us the range of the Nagoka phase, the level spacing, the level crossing. Okay, so using this technique, we can actually detect the rigidity of the Nagoka phase. We can tune the chemical potential, tune the potential well to be a smaller or larger value. If you make it smaller, then you push the electron to the 3 sides out of the 4 sides. then you become the antiparamagnetic state. Again, it's undoped. If you drag the potential to a larger value, you start to track 2 electrons to a single hole, and the remaining is a itinerary electron. In both cases, you will destroy the Nagauka phase. And that's what happens in simulation. You can see that in the red regime, you have Nagauka. Once we detune the potential for a single site, you start to deviate from Nagauka phase, and the gap will be asymmetric. And you have a slightly bigger one for the positive detuning and the smaller one for negative detuning. So this can be realized in experiments. You can track the difference between the diabatic state tuning and the adiabatic detuning. The range is smaller for the dV smaller than 0, dV negative, and the range is bigger for dV positive. We can also verify Nagauka transition using the angle detuning. That's related to the new interesting physics called the deep lattice theorem. So in a single hole in the 2D case, we have the interference of path to lead to the high spin state of the Nagauka theorem. But when we have a single hole in the 1D case, we have the deep lattice theorem regime, which tells us we always want to minimize the total spin, no matter what, in the open boundary 1D system. So that means if we tune the angle a little bit, we will destroy the path interference of the path. And the simulation tells us, indeed, if we detune the angle by only 0.3 degree, we can destroy the Nagauka phase because of the interference of the path. And that can also be verified by experiments. We tune it a little bit, you still see the separation of the two of the diabatic and adiabatic curves. But if we rotate the angle a little bit more, we will see them merge. Okay, so I want to finish my talk by putting the summary. I do not want to repeat. I basically discussed the 2 types of simulators and the 2 cases for the single hole physics.
Thank you. Talk is open to discussion. Yeah, please.
So in the Hubbard model, the kind of separate state fire from the super exchange or one fire from the super exchange, do you in a way recover local in Nagauka physics, or that would be totally incorrect picture and still a very big difference?
So you mean when we increase the temperature for the single band Hubbard?
Yes, and you go above the super exchange, so basically it's in the free, but then you have like one goes full locally, does it become like ferromagnetic? Does it resemble Nagauka phase, or that problem?
Not here, because the correlation is still not extremely strong. So the correlation is comparable to the bandwidth. So that the interaction, the super exchange interaction is still important. The interference of interference of the passes, they are quantum states. So they are quantum physics, they are not the thermal vibration. So you cannot protect the interference of the passes by increasing the temperature. So instead, the comparison of the kinetic energy you gain by the path interference is still smaller than the interaction you generated by the spin polygon. So this is really a good condition.
If I view your rating with 4 sides, right? Put
Yeah.
1 side, how long does the Nagauka survive?
I think it's equivalent to the 2D system, but the only difference is that in the 2D system we have the real geometry of the column. So the distance between the diagonal sides, they are a square root of the square root 2 instead of 2. But I think that Nagauka phase will still be there. So the Lattice theorem only works when you have open boundary one chain. It doesn't work when you have the theoretical one chain. If you have a very large 1D chain, yes, you will destroy the phase. There are no phases you can interfere. But for a 2x2 system, you still you regard the 2x2 as a 1D chain, you still have the same interference pattern.
So do you know how many sides you put and then break down?
I'm not quite sure, but
What the scaling is the following, right? Because you basically what you send me was you or the number of sides. So because you antikinetic state is lowered by super exchange times n, right? And kinetic energy is just T. So therefore, roughly you can say that you have to compare T versus J times n.
So in a real thermodynamic limit, you really need infinite field.
A quick question here. This 20%, is it, what is the size of your polaron? And my question was whether this 20% is coming from, when the density of polarons becomes such that there is overlap and that determines this number.
Yeah, that's a good point. So I really do not try to argue this is exactly the thing we should observe in solid state. In the simulation, we use the 4x4 theoretical boundary system, so there's the limited power you can collect in the game. And in experiment, it's a large harmonic trap, the scan the pixels of still a small regime. So it's really not the thermodynamic limit. We cannot consider the power on the number scaling with n or something. But since this is a temperature independent crossover, and it depends something for the breakdown.
Yeah, it's also very good.
Just a comment to add, right? When we do the straight state, we do indeed find that at 20%, that's when it starts to overlap.
Okay. It's also remarkably close to the Fermi surface restructuring that I talked about. So it would be good to correlate all of these things. Okay, well, let's thank Yao for a great talk and move to the next one.